So welcome to Math341 Lecture 7. This is going to be our second of two lectures on applications to modeling. So what I want to do today is just give you some sense of the types of problems you can look at and how you can use mathematics to either solve them or begin to work towards a solution. And the idea is to motivate a lot of the material we're going to be doing later in the semester. Why are we going to spend so much time developing? Well, if you have an idea of where you're going, this will give you some idea of what you want to decide to study. If you look at calculus, let's do the product rule today, let's do the quotient rule tomorrow, let's do the chain, things are not always done in that nice order. There are problems that inspired people, and those problems then led to the development of various types of mathematics. Right. So I want to talk today about continuous models. We were doing more discrete models last time, and we'll solve completely some continuous deterministic systems. These are wonderful, but unfortunately they don't always describe the real world. And that's where probability is going to come into play, where rather than having everything determined, you will have values that will be taken from some distribution. And that's going to be our goal to get to a point where we understand something like that. We'll discuss a little bit of general solutions, and then I think we'll have some time to get into a little bit of Zeckendorf decompositions. I talked a little bit about them last time. It's a nice way to lead into a lot of the nice distributions we want to study, as well as the central limit theorem. All right, so continuous systems. How many of you have taken a differential equation class? All right, not too many. So differential equations model a huge variety of phenomena. You have Newton's second law, F equals ma. Acceleration is the second derivative of position. We want to solve differential equations. So here is a standard one. F prime equals af of x with some initial condition. And typically, if you have one derivative, you need one condition. If you have two derivatives, you need two conditions. Your two conditions could be your value at two locations, or it could be maybe value and speed. So if we take the special case a equals 1, hopefully this looks a lot like the equation of f prime equals f. Oh, this is just my exponential function. So in that situation, the answer is just going to be f of x is c e to the x. And now when I take f equals 0, I'll get my value c. Right. So you've seen this before when looking at the exponential function. You just may not have seen it emphasized as solving a differential equation. More generally, if I have f prime equals a f of x, the solution will be c e to the ax. Okay? If a is positive, the solution is going to be exponentially growing. If it's negative, it's going to be exponentially decaying. Can anybody give me a physical example where you would have a positive or an example where you would have a negative? Something that's exponentially growing. Population, your bacteria, population, those will be exponentially growing. How about something that is exponentially decaying?
Radioactive decay.
Radioactive decay, excellent. So I actually spent a couple of summers working in a nuclear physics lab. So sometimes you have to do your experiments quickly. Francium, for instance, I believe has a half-life of 22 minutes. All right. So you can just check and say, if this is our proposed solution, if we take the derivative, does it work out? And again, this is the method of divine inspiration. If you have an idea of what the answer is, check and see if it works. All right. What if we had two derivatives? Your f double prime is some constant f prime plus bf. Well, this is similar to our difference equations from before. We can try something that's an exponential solution. So before, we had r to the n when we were trying to guess how to solve Fibonacci numbers. If we guess f of x is e to the rho x, I can view e to the rho x by grouping as e to the rho to the x. So the e to the rho is playing the role of r, and x is playing the role of n, which makes sense. Your n, which was discrete, is now becoming x, which is continuous. I'm writing r as e to the rho because it makes differentiation easier. You always want to work base e. You always want to do logarithms base e. And so if we now plug in two derivatives in one derivative, we get rho squared e to the rho x plus a rho e to the rho x plus b e to the rho x. Well, the e to the rho x is never 0, so I can cancel it. And we get rho squared minus a rho minus b equals 0. Oh, well, that just has roots rho 1 and rho 2. You can solve that with the quadratic formula. It's very, very similar to what we did for difference equations. The theory is very similar. And we get f of x as alpha e to the rho 1x plus beta e to the rho 2x. This is essentially saying this is a linear system. If I have one function that works, if I rescale the function by 5, I rescale everything by 5 and it's still a solution. That's where the alpha and the beta come from. If I have two solutions and I add them, it's also a solution. Right? So in general, you can have several variables and a lot of related quantities. So imagine now I have two systems of equations. I have f prime and g prime in terms of f and g. How many of you have seen maybe the Volterra predator-prey equations? So you might see something like this in a lot of like mathematical biology classes, where you have two populations, prey and predator. It's better to be the predator, and you want to see how the populations evolve over time. How would we solve something like this? Well, if you think back to linear algebra, before you got onto the matrices, you would often say, well, let me solve for one variable in terms of the other and substitute in, and let me try to eliminate the number of variables. So let me try to solve for g in terms of everything else. So g of x will be 1 over b f prime minus a over b f of x. I'm just solving for g. And now I can substitute into this equation, and I get something that only involves f and f prime. And I still have another derivative, fine, so I'll have two derivatives of f, not a big deal. And so when the dust settles, I now have a second order differential equation, but just involving f. I can solve for that, and I can play the similar game now, and I can then solve for g prime, or I can solve for g. So we can solve systems of equations like this very easily. Let me write this in a nice way, similar to how we did the Fibonacci's. We can do this with matrix form. So I'll have my vector will be my f of x, g of x. My matrix will be a, b, c, d. And then I get the equation b prime of x is a, v of x. So this looks a lot like what we just saw before. F prime of x equals a f of x. And this is the main reason I want to do this, is I want to just talk about how whenever you have a complicated problem, try to reduce it to something simpler where you have intuition. We know how to solve this, so all we're doing now is, now we're going to let little a be a matrix, and we'll let f be a vector. Well, why don't we just guess that the solution is exactly as before? And so we have to be a little bit careful now, because now v of 0 is going to be a vector and not a scalar. So when we had the c e to the ax, that's the same as e to the ax times c. The order doesn't matter. But now the order in which I put vectors and constants matter. And if I just try this, we talked a little bit about the matrix exponential last time. Formally, you can define the exponential of a matrix if it's square. You'll have this infinite series, and it turns out no matter what matrix you put in, the series converges. Very nice when that happens. And this is the solution. And so we can justify all the stuff. And then I mentioned last time my favorite formula, or one of my favorite formulas, the Baker-Campbell-Hausdorff formula. As to the difficulty, e to the a times e to the b is not e to the a plus b. But fortunately, a lot of the matrices here will convert. Will commute. All right. So an application, Battle of Trafalgar. Anybody ever study the Battle of Trafalgar? Okay. Is there anybody who is bothered by the outcome of the Battle of Trafalgar? Okay. So to celebrate the 200th anniversary of the Battle of Trafalgar a few years ago, they reenacted it. But so as to make sure nobody would feel bad, they didn't have the British versus the combined French-Spanish force. They had red versus blue. And people weren't supposed to know which side was which. So we will just do that, and we will, for the both, I will often talk about red and blue and not mention British and French. There will be a couple of times when I will slip and whatnot. All right. So this is one of the most important naval victories of all time. Basically, the British smashed the combined Spanish-French fleet. This was extremely important for England, which is a... I'm sorry? What kind of country, though? Island country, right? For Britain, their fleet, their navy matters. For a long time, Britain used to have a policy that their navy had to be strong enough to go to war against the next two most powerful navies. And then eventually, as World War I gets closer and closer to happening, with the armaments race, it gets to the point where they can no longer do that. And it's like 5/3. The ratio changes a little bit. Right before World War I, there was an interesting negotiation between Winston Churchill, I think he was one of the Sea Lords of the Admiralty at the time, and Parliament. I think Churchill wanted 6 of the dreadnoughts built, Parliament wanted 4, and they compromised on 8. It was a very interesting negotiation session. They eventually convinced you, yeah, we need a lot of these ships very quickly before the war breaks out. So 27 British ships of the line, led by Admiral Lord Nelson, aboard the HMS Victory, he was very confident, defeated 33 French and Spanish ships of the line. Now, there's a lot of assumptions when you try to model a battle. Right? The first thing is, do you assume that the British and the French and Spanish ships are all equally good? Not necessarily. You know, the British might have better sailors, they might have better ships, they might have cannons that have more powerful range. So there's a lot of different things you can do. I'll try to keep the model simple. So again, we'll have R of t and B of t, the red and the blue sides. And then again, whenever possible, you want your notation to be good. I'm trying to do things in color so you can quickly look down. And I have these models. So N and M are going to be the effective fighting values. N will be of the red fleet, N will be of the blue fleet. And I'm saying, here's my differential equations. The rate of change of the number of blue ships is going to be negative N times the number of red ships. Does this make sense? Yeah, the more red ships I have, the more blue ships are going to be lost. And I'm just assuming that it's nice linear right now. So if you double the number of red ships, that should double the amount of salvos being fired at the blue ships. It should double the amount of damage. This is a simple model. If you have too many ships, they may not all be able to fire at the same time. They may get in each other's way. If you look at museums, why do museums have security guards? Why do museums have security guards? Yes?
So people don't steal the exhibits?
So people don't steal the exhibits. There are some exhibits which I don't think you actually need a security guard for, but that's another story. If you only have one security guard, is the security guard going to do a great job of protecting you? No. So as you start adding security guards, it gets better and better and better. But then at some point, you have so many security guards that adding the additional ones is not going to be giving you the same marginal benefit as the beginning. You always want to get a sense of how reasonable are the models. This is a crude model. And this may break down in some extreme cases. But as a start, let's see what happens. Is it still in focus? Yeah, I was wondering about that. All right. So we can solve this using techniques from before. What do you expect is going to happen to the red fleet and the blue fleet over time?
They're going to decrease?
They should be decreasing, right? Do you expect the red fleet or the blue fleet to get larger as the battle rages? Who knows the naval history? Do fleets ever get larger in old battles? Yes. How do they get larger? Yes. This will not happen in 20th or 21st century naval engagements. But in the old days, you could actually capture the other side's ships and use their own ships against them. So there would be times when you would actually scuttle your own ship rather than having it used against you. We will assume that's not going on, but there are definitely boarding parties and there are definitely battles to take control over ships. With the battleships and the aircraft carriers of today, that's not going to happen. So we will assume that the model we have, we're going to be in cases where the blue and red ship fleet sizes will be going down. So if we take another derivative, we get the second derivative of blue equals negative n times the first derivative of r. Oh, well, good, we know what the first derivative of r is in terms of blue. And so now we have an equation just for blue. And similarly, we can get an equation just for red. We now know how to solve this. We just solved second order differential equations a few moments ago. And so we get the following solutions. The cardinality of the blue fleet is going to be beta 1 e to the square root of nmt plus beta 2 e to the negative square root of nmt. What can you tell me about these coefficients beta 1, beta 2? Yes?
Beta 1's probably negative.
No. You're close. Not negative.
Oh, between 0 and 1.
Nope. So imagine both beta 1 and beta 2 went 0. As t gets very, very large, what does this factor go to? What does this factor go to? Plus infinity. Right? This is supposed to model something realistic. The only way this can work is what should beta 1 be? Beta 1 has to be 0. When I'm looking at what happens to the British fleet size, the British fleet size is not going to go to, just say British, sorry, the blue fleet size is not going to grow to plus infinity. So the only solution that's physically realistic is the second one. You often have extra solutions. If you've ever done an old algebra problem where you have a square root and you square both sides, yes?
When you're making a model,
Mm-hmm.
is it best to, like, when you're halfway done, cut something that doesn't make sense? Or in this case, when that happens, go back and start from the beginning?
Well, the point is, we actually have the freedom of what beta 1 is. And then we can see, because this has to describe, we know that in the limit, at least one of the fleet sizes should go to 0, and the other one should be no larger than you start with. So we know that both beta 1 and alpha 1 have to be 0. So the model is not unrealistic. It's just that at this point, not all of the possible solutions are actual solutions. If you go back to trying to solve certain equations involving a square root, you solve this by squaring both sides, and this often introduces a phantom solution or an extra solution. You sometimes have these problems in calculus where you're trying to figure out what's the length, and the length is either 2 or negative 8. And you realize the length is probably not negative 8, that as we were doing the algebra, we introduced an extra solution. It's the same thing going on over here. The real thing that's interesting is b prime over b equals r prime over r. This leads to n times r squared equals m times b squared. This is called the square law. And it basically says, if you have different effectiveness of the forces, how many reds do you need to equal how many blues? So yes?
Just beta and alpha, those are both real numbers?
They're both real numbers, yes. And you can always choose them to match the initial conditions. How many ships do we have at time 0? B0 and R0. Well, at time 0, this term is just 1, so beta 2 will just be B0. And alpha 2 will just be R0. So basically, if the blue ships are 4 times as effective as the red ships, you would have to have a red fleet that's twice as big. That's the value of this. It gives you some sense of how much we need to equate things. All right, so Nelson was outnumbered. How can Nelson win? All right, so here is essentially what's going on. He's going to have his fleet coming in 2 directions. He's going to try to split the Spanish-French lines. Now, this is actually a really good configuration for the Spanish-French fleet. What's good about that configuration? Yes?
All their ships can fire.
Yes, all of their ships can fire. And can all the British ships fire on the French and Spanish ships? No. Basically, only the ships at the beginning. So the other ships you have to worry about hitting your own compatriots. In World War I, initially planes were just used for reconnaissance. And there were so few pilots. People were so happy that they'd wave to somebody from the other side. It's nice to see you up in the sky. Then eventually they decided, well, no, actually, we probably shouldn't be waving to the enemy. So they would start throwing things. They would throw bricks and stuff at people. And they would start shooting guns at each other. And so they were trying to figure out where to put the guns to shoot. And a lot of times people would shoot themselves down. They would shoot, it would hit their own propeller. And it was a great invention by one of the Frenchmen to time the shots with the propeller blades so that you could have the gun right in the center and you can line up and shoot and not actually hit yourself. But in this attack right now, the ships at the beginning are going to bear the brunt of the assault from the French and the Spanish. And basically, the idea is, we destroy the ones in the beginning, very few things can fire at us, and then we'll get the next ones and the next ones and the next ones. This is a dangerous strategy. This is called crossing the T. It's a giant T over here that all of these ships can attack. Nelson's plan is to get his forces in like this and split the other fleets, and then he'll have the T's. And so he has 40 ships against 46. This was in his preliminary thoughts as to what the battle would look like. The actual numbers were slightly different, but the idea is roughly the same. And so what he wants to do is he wants to split the enemy fleet into 2 parts. And he's going to have a small subset of his ships hold a subset of the enemy at bay, while the majority of his ships take on a good chunk of the French-Spanish fleet. And then once they dispatch that, then they'll swing back and get the earlier parts. So if you assume that the ships have equal fighting abilities, there were 46 French-Spanish ships, 40 British ships. The effective strength of the 2 fleets shows you that the French-Spanish force is numerically stronger. And again, this is under the assumption that the French-Spanish ships are as good as the British ships. But just for simple analysis, let's do that. So if they just fight directly, you can see that Nelson's forces are outmatched. His idea was to split his fleet of 40 into 32 and 8. And the idea was to split the French-Spanish fleet into two sets of size 23. Which would you rather be if you were a British sailor, in the 32 component or the 8 component? All right, so it's pretty clear you would much rather be in the 32 component. These 8 ships, their task is to keep 23 ships at bay, while Nelson's 32 take on the 23. And then, if they can dispatch them quickly enough, they will then come to the aid of whichever of the 8 ships are still remaining. When you look at it like this, it's a slight British advantage. This is much better than a huge British disadvantage of 500. So Nelson had a really good grasp of how to divide things. And so, in terms of what actually happened, we mentioned it was 27 British ships at the end of the day versus 33 French and Spanish ships. The Franco-Spanish fleet lost 22 ships without a single British ship being lost. So in terms of just the actual values of so this is Trafalgar Square, the British 0 of 27 ships, 1,666 dead or wounded. Franco-Spanish 22 of 33 ships, 13,781 captured, dead or wounded. This was not just a victory. This was a crushing defeat. Now, there are a couple of issues with this. The first is everything is completely deterministic. Fortunately, most of you are not going to be involved in battlefield situations. It is extremely unlikely that any battlefield situation will be perfectly deterministic and everything will go according to plan. So you need to introduce levels of randomness. Do you really think those 8 ships can hold off the 32? I'm sorry, the 23. What's your probability of how long they hold? Yes?
Why was it that the 8 ships were able to all survive during that first phase? It seems like it would have been really unlikely.
So a lot of it will come down to, I think, the quality of the ships, the quality of the crews of the ships. But I agree that the 8 holding off. I don't know the full details of the battle as to how quickly did the 32 dispatch the others. And again, this was what the battle plans were. I doubt the actual battle went like this. And so the question is, were the 8 always by themselves, or did some of the other British ships see that some of their brethren were in trouble and come to their aid? A lot of it could come down to how the wind is blowing. Because back then everything is powered by wind, and you could all of a sudden be in a position where you can't maneuver as well. So there's a lot of details for stuff like this that are beyond the scope of this class. I want you to get a sense though of how you can apply math in different settings. This is solving simple differential equations. We've seen how to do this. It's related to stuff you've already known, and we've seen that there's a solution involving a matrix exponential. Well, now we need to do a matrix exponential where things are variable. We talked before with the real problem about how to do this. And we had a product of matrices with random entries. Now you would need an integral of matrices with random entries. And I just want you to get a sense of where all the math goes. All right. Any questions on Trafalgar? All right, so if there's time, I will talk a little bit about the Battle of Midway at the end. I want to now really go into Zeckendorf decompositions. This is something I've done with a lot of my small students. For those of you who are thinking about maybe a career in mathematics and want to try your hand at summer research, I'm happy to chat with you more about what my summer students and I do. So we've talked a little bit about this yesterday. I'm going to quickly review it. The Fibonacci numbers are defined by the following recurrence. Each number is the sum of the previous 2. I start with a 1 so that I have the following beautiful theorem. Every positive integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. And we talked about this last time, 51, since we have a guest. You do the greedy algorithm. You take the largest Fibonacci number less than equal to your number, 34. I have a remainder of 17. All right, 17, large Fibonacci number less than equal to that is 13. If I could have taken 21, I would have taken 2 Fibonacci numbers that are adjacent, and then I could have taken their sum. And that would have contradicted 34 being the largest Fibonacci number. So as you continue this process, you end up getting a decomposition of 51 as a sum of non-adjacent terms. We talked about the conversion factor between miles per hour and kilometers per hour by just the fact that the golden mean is approximately the conversion factor between miles and kilometers. All right. So I think I showed you this plot before, but if not, this is looking at how many summons we have. And the reason I really want to talk about this is a huge part of this course is learning what's the right question to ask. I want to look at how many summons my number has. And I want hopefully there to be some kind of limiting behavior. What I'm doing is I'm choosing a number randomly between fn and fn plus 1. What this means is all of my numbers are about the same size. So you can probably figure out what year this data is from. Right? This is probably something I did in 2010. The 2010 Fibonacci number is about 10 to the 420. These are large numbers. This is not going to be an exhaustive search. I am not going to do 10 to the 420 calculations. So you do a couple million. Do you think that the average number of summons for a number between fn and fn plus 1 depends on n? Do you think you have maybe more summons if n is 1,000 than if n is 10? What's the maximum number of summons you could have if n equals 10? I'll accept two answers. What's the most summons you could have if n is 10? 10, right? You can't have more than 10 summons. But we know something about the decomposition. What do we know about the decomposition? No adjacent terms. So we can refine the 10 down to we could have 5. Right? But we know if n, whatever n is, we have at most n, or even better, at most n over 2 summons. So if n is 10, or another one is n is 1,000, we would probably expect a very different number of summons. So if I'm trying to see what kind of behavior is going on, the behavior could depend on where we are. So by looking at this, all of my numbers are roughly the same size. You want to compare apples and apples. This is going to be one of the themes of the course. When we get to the central limit theorem, we have sums of random variables. We're going to standardize them. We're going to subtract off the mean. We're going to divide by the standard deviation. So by looking at this, all of my numbers, their first summoned is always going to be fn, because they're in this interval. So I'm looking at all numbers whose, okay, this is a good way to look at things that are going to be comparable. All right. Did we talk about the Fibonacci numbers? This is an alternate definition. All right, so I'm not going to do that one again. I'll just pass through this. All right. So what I want to do is I want to give you a sense of why we have this Gaussian distribution. And this is going to be a way to talk about the central limit theorem. This is the highlight of the course. Is either I'll say mostly proving the central limit theorem. We will prove it in some special cases. To prove it in general, we really need some results from complex analysis. But I can at least prove it in some special cases and motivate why it might be true. A huge thing that I always want you to be thinking about is if you have a problem, if you have a system, think of an easier system to study. So when we look at the Fibonacci numbers come from a recurrence relation. I could consider a more general recurrence relation where I have different choices of the C's, and I have maybe some fixed depth, length L. And I have some initial conditions. And it turns out if all the C's are non-negative integers, and if at least C1 is positive, then you have a generalization of Zeckendorf's theorem, that you will always have a unique legal decomposition. And you'll also have a central limit type theorem. You'll have the number of summons will become Gaussian. So can anybody think of a really simple recurrence relation we should look at to build intuition? I'm assuming most of you have never seen Fibonacci numbers being used to represent numbers. How have you represented numbers before? What did you learn in school? Counting on fingers. So what's that called? Decimal. Right? You've all seen decimal systems. Right? So let's say hn plus 1 equals 10 hn. This is base 10. If you were a computer, what would you do? Base 2. Or maybe base 8, base 16, depending on something. But for the most part, base 2. So hn plus 1 is 10 hn. This is the decimal recurrence. Now, what does it mean to have a legal decomposition? It just means I'm writing you in decimal. If I ask, how many summons do you have? It's just adding up the digits. So if I take 2018 and write 2018 in decimal, what's the sum of the digits? For 2018? 11. So what I'm basically just asking is, if you choose a large number randomly between 10 to the n and 10 to the n plus 1, what's the sum of the digits of your number? That's going to be normally distributed. And this is the precursor to the central limit theorem. Right? So if we take some number in our interval, the first term is hn. So let's let ai be the corresponding random variable that goes with little ai. So ai is our digit, capital AI is the random variable. This is the notation we'll be using all semester. Capital letters are random variables, lowercase is values. The AIs are independent. It's just whatever digit you want. I want to have a 3 here, I want to have a 5 here, I want to have a 7 here. Are all the A's the same, or is one A slightly different from all the others in terms of what values it can take on? Yes?
The first one can't be 0.
The first one can't be 0 because we're assuming we're in the interval, 10 to the n to 10 to the n plus 1. But other than that, they're all the same. And if n is huge, the fact that the first one can't be a 0 is negligible. So for large n, the contribution of an is the largest one is immaterial. All the other ones take on the values 0, 1, 2, 3, all the way up to 9 equally likely. Their average value is 4.5, their variance is 8.25, and then this is just the central limit theorem. I'm now summing a bunch of independent, identically distributed random variables. And so by the central limit theorem, this will become a Gaussian. So the Fibonacci result, you can actually justify it. You can get some sense of why it might be true by looking at a simpler case. All right. So I want to talk about another problem, distribution of gaps between summons. And this is related to a lot of really good mathematics. So imagine I have a number which is f1 plus f8 plus f18. Then I have two gaps. I have the gap between these two summons, which is 10, and the gap between these two summons, which is 7. And I want to know how are the gaps distributed. So I can let Pn of g be the probability that a gap in a decomposition is of length g. So there are two ways to do this. One way is a lot easier than the other. What I can do is I can fix my interval, and for each interval I take my numbers, and for each number I look at how many gaps does it have of length 1, of length 2, of length 3, of length 4, and I put all that in a giant bin. And then just see what fraction of the gaps in that bin are length 1, what fraction of the gaps in that bin are length 2. So I'm looking at all numbers together. The other thing you could do is you could choose a number randomly in here and look at the distribution of the gaps. The hope, and it turns out to be true, is that most numbers, once n is large, the distribution of their gaps is close to the distribution of the average gaps when you average over everything. Can somebody give me a number in here that has only one summand? Fn. So if I want to, it has no gaps. Can somebody give me a number that has two summands? I'm sorry?
Fn plus 1.
How are you saying Fn plus 1? Are you saying like this?
No.
Or are you saying one more than this?
One more than this.
Yeah, so that would be Fn plus F1. That will have two summands. Fn plus F2 will have two summands. Fn plus F3 will have two summands. If I wanted to do three summands, I could do maybe Fn plus Fn halves plus F1. Most numbers will have approximately n over 4 summands. So if you just have a few summands, it's going to be very different behavior. So what you get is you no longer get that every number will have a distribution of gaps that's similar to every other. But you'll have almost all numbers will have their distributions very close to each other. That most numbers are common. A good example is looking at the air molecules in this room. Is it possible that all the air molecules could be on your side of the room? It's possible. I'm not worried. I don't have an extra oxygen tank on me for that eventuality. I've got the munchkins. I figured you'll come and save me. Right? Why am I not worried? Well, if we assume each molecule has a 50-50 chance of being in the front or the back, if n is huge, You expect to have n over 2 in each half, and the fluctuations turn out to be on the scale of square root of n. We'll see that throughout the semester, that things are often at the square root level. Well, if I look at square root of n divided by n, that fraction is negligible. Does anybody know roughly how many air molecules there are in this room? Roughly. Yes?
10 to the 25, 10 to the 30.
Something like that. Your Avogadro's number 10 to the 23 number of molecules in a mole, right? You know, somewhere between 10 squared and 10 to the 7 moles I think is reasonable for this. We have somewhere between 10 to the 23 and 10 to the 30 molecules in this room. I'm really not worried about the square root of that over that. 10 to the 15 over 10 to the 30 is negligible. So with very high probability, if you were to just randomly choose where each air molecule were and then say, go, lecture, it is unlikely that I will be collapsing from lack of air. Most configurations will be close to the average. Will there be extreme cases? Absolutely there will be extreme cases. But those extreme cases are so rare that they really dwarf. Okay. So the question is, what can you tell me about the distribution of the gaps? And so we've talked a little bit about this. We talked about this last time in terms of how you want to view things. The last thing which I will mention is we also proved results about the longest gap. And this is in some sense similar, bless you, to what we were doing with the Vegas problems in roulette. What's the probability of getting 5 consecutive blacks in a row, 5 consecutive reds in a row? You can calculate the distribution of the longest gap, and what I love is the answer. The probability that the longest gap is at most, say, f of n, is e to the negative e. It's one of the only times I know where an exponential of an exponential arises in a meaningful way in mathematics. This is very much related to just tossing a coin and asking, what's the probability that my longest run of heads is a certain size? When people are making up fake data, one of the experiments you often have your probability students do is half of you flip a fair coin 100 times, half of you make it up, and then you give it to me, and I'm supposed to determine which one were you. Were you making it up, or were you actually flipping? And if you flip it, or your sequence has to be of length 100 or 200, it's very hard for me to get it wrong with the probability I know. How many heads should you have roughly if you flip it 100 times? 50. Everybody knows that. But people don't know what should be your longest run of heads. And people have much less of a sense of randomness for something like that. Later in the semester, I will talk to you about Benefit's law of digit bias, which is used by the Internal Revenue Service to detect tax fraud. So I've actually given talks at IRS headquarters on stuff like this, have a lot of students working on projects along those lines. Right. I'm not going to go into all the details of proving what my students did, but what I want to do is I want to give you a theorem, which is a theorem in the book. This is the cookie problem, which we describe in the book, because I love this mathematics. I love this way of looking at problems. So the number of ways of dividing C identical cookies among P distinct people is C plus P minus 1 choose P minus 1. And this is extremely useful for solving a lot of these problems. And so here's the proof. Imagine we have C plus P minus 1 cookies in a line. Is there anybody who does not know who Cookie Monster is? Okay, so Cookie Monster is a beloved character from Sesame Street. He loves to eat cookies. In the last few years, political correctness has attacked Cookie Monster, and he now has to sing that cookies are a sometimes food. I don't know if he has to sing glories of vegetables. I don't know if it's gone that far. But the original classic Cookie Monster was always up for eating cookies. There's a great episode where Cookie Monster meets the Count. And Cookie Monster wants to eat the cookies, and the Count wants to count the cookies. And they find a solution. What is the solution?
Does it count how many?
Yes, the Count counts how many cookies the Cookie Monster eats. And peace is restored. So imagine we have 8 cookies. And we have 5 people. So I consider 8 plus 5 minus 1. I consider 12 cookies in a line. And now Cookie Monster eats P minus 1. Cookie Monster comes and he eats 4 cookies. By eating 4 cookies, he puts in 4 dividers. And that splits the set into 5 parts. Everything up to the first cookie goes to the first person. Everything between the first and the second eaten cookie goes to the second person. It's not their day, they get nothing. Everything from the second to the third goes to the third person, to the fourth person, to the fifth person. This is proof by story. There's a one-to-one correspondence with the number of ways Cookie Monster can eat 4 cookies from 12 as to how I can divide 8 cookies among 5 people. And there's a lot of related questions you can do this. We have some parts in early probability where we need to do combinatorics. This is a terrific combinatorial problem. Now, some people may think that this problem should not allow a solution like this. Right? What's the unsatisfying part about this solution? Why might some people think that this solution is unfair? Yes? Some people, I'm sorry?
Get stuck without cookies?
Some people get stuck without cookies. This poor second person has no cookies. Well, this person got 3 cookies. That's not fair. So you might want to have almost like a minimum wage, a minimum cookiness. Everybody must get at least 1 cookie. How would you solve this problem if now I required everybody gets at least 1 cookie? So we just figured out how to divide C cookies among P people. Yes?
Just take out the P cookies at the beginning.
Just give everybody a cookie initially. And so all I have to do now is I have to divide C minus P remaining cookies. Right. Now, actually the munchkins are a really good example. So I'm giving munchkins to you. You guys all have freedom. But there is a chance that some munchkins will be left over, in which case my kids will be very happy because they will have munchkins for breakfast tomorrow. What if we don't have to divide all the cookies? This is how many ways we can divide the C cookies among P people if every cookie is divided. What if we don't have to divide all the cookies? What's the answer?
Just add another person.
You add another person. Right? If we're dividing C cookies among P people and we don't have to allow all the cookies to be divided, well, we could figure out how many ways are there when you divide no cookies, 1 cookie, 2 cookies, and you'd have to sum this. So you would sum, we've got a binomial sum where the numerator, where the top is changing. The solution is you imagine an extra person. We will name this person Cam Kayla. Okay? And so whatever is left over goes to Cam Kayla. You just add an extra person. And now all of a sudden you've proven a binomial identity. This sum with numerator changing is just going to be C plus P choose P. This is the power of proof by story. This is why I wanted to spend time doing this early in the semester. If you can look at problems the right way, it is incredible what you can do. It is often very hard to look at problems the right way. Okay? And so this is just making it a little bit more formal. You don't actually have to treat everybody fairly. You could say, well, this person's a pre-fosh. We need to make sure they get extra cookies. We need to make sure they get at least 3 cookies. And this person's a senior. Oh, they're about to go off to the real world. We want them to remember Williams fondly. We also have to make sure, we'll make sure they get at least 2 cookies. You could have people treated unequally, and you can assume person I gets at least CI cookies. Yes?
The last part, when you're talking about adding an extra person,
Yes.
I was kind of confused in that. I didn't really follow.
Okay, so what we are wanting to study, let's do it down here, is we have a sum, C goes from 0, I'll call it to big C, of C plus P minus 1 choose P minus 1. And so we have big C cookies, and I could give out no cookies, 1 cookie, 2 cookie, all the way to giving up all the cookies. So imagine we have 4 people. So maybe big C equals 8. I give 1 cookie here, 2 cookies here, I really don't like the third person, and then I give 3 cookies here. That's only 6 cookies. What I can do is I just imagine there's an extra person. And however many cookies I haven't given out, I just give those cookies to that extra person. So I have to get up to 8 cookies. So if I've given out 6 cookies here, how many cookies does this extra person get? 2. So this is going to just be, I now have big C cookies, and now I have P people. I have P plus 1 people. So it'll be C plus P p plus 1 minus 1, choose p plus 1 minus 1. And that's just the proof by story. Any other questions on this? So the difficulty is not in a certain level of fairness and making sure everybody gets a certain number of cookies. The lower bounds are easy. The difficulty is if we want to have upper bounds. That you can't have more than 5 cookies. There's no nice way to put that in and get a nice clean answer like this. Sadly, this is how math is typically. You don't always have nice answers. There is a solution involving something called inclusion, exclusion, adding and subtracting probabilities, which we'll see more a little bit later. So it turns out you can use this to prove that every number can be written uniquely as the sum of non-adjacent Fibonacci numbers. And I just wanted to do this to just give you a sense of how recurrence relations can occur in so many different places. So we're going to let P and K be the number of integers in here that have exactly K summands in their Zeckendorf decomposition. Every number is going to be decomposed. It turns out that the decompositions are unique. That's not hard to show. If they had 2 different decompositions that were the same, do they have the same largest term? If yes, subtract that, and by induction you're done. If not, they will be different sizes. So you can split every number based on how many summands it has. This is very similar to the Larry Bird Magic Johnson game from the beginning. On what shot did Bird win? So now we split up and we count how many times do we have exactly K summands. And so if we are in this interval, we have to have Fn as our largest summand. And then we'll have Fk minus 1 all the way down to F1. Okay? And so now what we can do is we can try to count how many ways are there. Well, I'm choosing a bunch of indices. And my indices, they start at 1, it ends at n, and each one of these gaps must be at least 2. This is the cookie problem. You should never try to follow algebra too closely at this point. It just should be big brush stroke. Let's let D1 be I1 minus 1. This is the excess over where the first index must be. The second index must be at least 2 more than I1, so let's write D2 as I2 minus I1 minus 2, and in general, Dj will be Ij minus 1 minus 2. We're subtracting off how many cookies each index must get. And if I add all of this up, I've got to get to n minus 2k plus 1. You can see it's just a cookie problem, and we get that the number of ways of having exactly k summands is this binomial coefficient n minus k, choose k minus 1. Alright, so I will end with a proof that this converges to a Gaussian. So we've talked about the gamma function, which generalizes the factorial function. N factorial is about n to the n e to the minus n squared of 2 pi n. We know that the number of numbers that have exactly k summands is given by this binomial coefficient. It turns out it's a little bit easier to look at having n plus 1, not n. And I just have to look at, this is the number of numbers, and then I divide by how many numbers are in my interval. My interval is now going from fn plus 1 to fn. I'm sorry, fn plus 1 to fn plus 2. The number of numbers in that is just fn. So all I have to do is I put in the factorials, and then I just go through and do the algebra. Or better yet, I have my students go through and do the algebra. They keep doing the algebra, and then finally, when the dust settles, it ends up as a normal. There are better ways of doing this, but this is the first approach. Step 1 is solve the problem. Step 2 is find a better solution to the problem, which generalizes. All right, so this is a good place to end. So I will stop this